This is section 11.2, part B, expected counts in the ChiSquare statistic. In the wine example in the previous section, the null hypothesis is that there is no difference in the distribution of wine purchases at this store when no music, French accordion music, or Italian music is played. If the null hypothesis is true, the observed difference in the distributions of wine purchases for the three groups are due to the chance involved in the random assignment of treatments. The alternative hypothesis says that there is a difference, but does not specify the nature of the difference. So our alternative hypothesis would be there is a difference in the distributions of wine purchases at this store when no music, French accordion music, or Italian string music is played. Any difference among the three actual distributions of wine purchases when no music, French accordion, or Italian string music is played means that the null hypothesis is false and the alternative hypothesis is true. The alternative hypothesis is not one-sided or two-sided. We might call it many-sided because it allows any kind of difference. With only the methods we already know, we might start by comparing the proportions of French wine purchases when no music and French accordion music are played. We could similarly compare other pairs of proportions, ending up with many tests and many p-values. This is a bad idea. The p-values belong to each test separately, not to the collection of all the tests together. So think of the distinction between the probability that a virtual basketball player makes a free throw and the probability that she makes all her free throws in a game. When we do many individual tests or confidence levels, do not tell us how confident we can be in all the inferences taken together. Because of this, it is cheating to pick out one large difference from a two-way table and then perform a significance test as if it were the only comparison we had in mind. For example, the proportion of French wine bought under the no music and the French accordion music treatments are about 36% versus 52% respectively. A two-sample z-test shows the difference between those proportions is statistically significant with a p-value of 0.039. If we make just this one comparison. But we could also pick to do a comparison that is not significant. For example, we could have picked the proportion of Italian wine purchased with no music or Italian string music playing, which is 13% and 22%. These two proportions do not differ statistically with a p-value of 0.107. So individual comparisons can't tell us whether the three distributions of the categorical variables, in this case, how much wine was bought, are significantly different. The problem of how to do many comparisons at once with an overall measure of confidence is all our conclusions is common in statistics. This is the problem of multiple comparisons. Statistical methods for dealing with multiple comparisons usually have two parts. First, an overall test to see if there is good evidence of any differences among the parameters that we have to compare. A detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. The overall test uses the familiar ChiSquare statistic and distributions. But in this new setting, the test will be used to compare the distributions of a categorical variable for several populations or treatments. The follow-up analysis can be quite elaborate. We will concentrate on the overall test and use data analysis to describe the nature of the differences. So when we want to find the expected counts in the ChiSquare statistic, to perform a test, we're going to do two hypotheses. Our null hypothesis is that there is no difference in the distribution of the categorical variables for several populations or treatments. And the alternative is that there is a difference in the distribution of categorical variables for several populations or treatments. We compare the observed counts in a two-way table with the counts we would expect if the null hypothesis were true. Finding the expected counts is not that difficult, as the following example illustrates. So the null hypothesis is that the wine and music experiment is that there is no difference in the distribution of wine purchases in the store when no music, French accordion music, or Italian string music is played. To find the expected counts, we start by assuming that the null hypothesis is true. We can see from the two-way table that 99 of the 243 bottles of wine bought during the study were French wine. If the specific type of music that's playing has no effect on the wine purchase, the proportion of French wine sold under each musical condition should be 99 out of 243, or we would expect about 40.7% of all the wine that is purchased to be French wine. For instance, there were 84 bottles of wine bought when no music was playing. We would expect that 99 out of 243 times the 84 bottles, that 34.22 of those bottles should be French wine on average. The expected count of French wine bought under the other two music conditions can be found in a similar way. So again, we're looking at this total. Out of the total number of bottles purchased, there were 99 French, so that's where we're getting this proportion. And then you're going to multiply it by, while French music was playing, there were 75 bottles purchased, so we're going to multiply by the 75. And we would expect that 30.56 of those bottles would then be French wine during that time. And again, we're still taking that same proportion, but when Italian music was playing, there were 84 bottles purchased, so we would expect out of those 84 that 34.22 of them were French wine. We repeat this process to find the expected counts for the other two types of wine. The overall proportion of Italian wine bought during the study is 31 bottles out of the 243, or 12.8%. So the expected counts for Italian wine bought under the treatment are, with no music, we would expect 10.72. With Italian music, we would expect 10.72 bottles. And during French music, we would expect 9.57 bottles. And again, we can do the same thing for other wines that are purchased. Out of the 243 bottles that were purchased, 113 of them were other types of wine. And again, you would multiply each of those by how many total bottles were purchased during those musical types to figure out the expected values. So the following table summarizes the expected counts for all three treatments. Note that the values for no music and Italian music are the same because 84 bottles of wine were bought under each condition. We can check our work by adding the expected counts to obtain the row and the column totals, as in the table of observed counts expected for small round-off error, such as 75.01 rather than 75 for the total number of bottles of French wine that are sold. Let's take a look at the two-way table from the wine and the music study one more time. In the example, we found that the expected count of French wine bought when no music was playing was 99 over 243 times 84 bottles to give us 34.22 expected bottles of French wine. We mark the three numbers used in this calculation in the table. These values are the row total for French wine bought, the column total for wine purchased when no music was playing, and the table total of wine bought during the experiment. We can rewrite the original calculation as just doing 99 times 84, the totals out of those two, that row and that column, and then divide it by the total of the table. So this suggests a more general formula for the expected count in any cell of a two-way table. You're going to do your row total times your column total divided by the table total. So to find that expected count, again, if it's in a two-way table, to find the expected count, you can do the row total times the column total divided by the table total. All the expected counts in the music and wine study are at least 5. This satisfies the large sample size condition. The random condition is met because the treatments were assigned at random. What about the independent condition? We are comparing 3 independent groups in a randomized experiment, but our individual observations, each wine bottle that is sold, independent. If a customer buys several bottles of wine at the same time, knowing that one bottle is French wine might give us additional information about the other bottles bought by this customer. In that case, the independent condition would be violated. But if each customer buys only one bottle of wine, this condition is probably met. We cannot be sure, so we will proceed to infer with caution. Just as we did with the ChiSquare goodness of fit test, we compare the observed counts with the expected counts using the statistic of ChiSquare equals the sum of all of our observed minus our expected squares divided by expected. This time, the sum is over all cells, not including the totals, in the two-way table. So the table below shows the observed and expected counts for the wine and music experiment. Calculate the chi-square statistic and show your work. So we can start with the French wine when no music is playing. So you would do the observed minus the expected, so here and here, squared all over the expected, plus, next we can do French with French, so we would do 39 minus 30.56 squared all over 30.56, and you would keep doing this for all the values in the table that are not totals. So everything in here, you should have 9 of those that you're adding together. And that total is your chi-square statistic. And that total for this one would be 18.28. When you take your AP exam, in the do step, you are not required to show every term in the chi-square statistic. Write the first few terms in the sum and the last term separated by ellipses. Is considered showing work. So as you can see, we didn't write all 9 values. We wrote the first couple plus ... plus another one, and then we wrote the last one to show what our method was, but you don't actually have to write every single step down. And that goes for the calculation part and when you actually get the values. As in the goodness of fit test, you should think of the chi-square statistic as a measure of how much the observed counts deviates from the expected counts. Once again, large values of chi-square are evidence against the null hypothesis. The p-value measures the strength of this evidence. To find the p-value corresponding to the chi-square of 18.28 in this example, we need to know which chi-square distribution to use. We will get to that shortly. So let's check our understanding for what we've done so far with this. In the previous Check Your Understanding, we presented data on the use of Facebook by 2 randomly selected groups of Penn State students. Here are the data once again. Do these data provide convincing evidence of a difference in the distribution of Facebook use among students in 2 campus settings? State appropriate hypotheses and alternative hypotheses to a significance test to help answer this question. So remember, the null hypothesis is always that there is no difference, and the alternative hypothesis is that there is going to be a difference. So the null hypothesis is there is no difference in the distributions of Facebook use between students at Penn State's main campus and its Commonwealth campuses. The alternative is that there is a difference in the distribution of Facebook use between students at Penn State's main campus and its Commonwealth campuses. Do these data provide convincing evidence? So this time we're going to calculate the expected counts and you're going to show your work. Remember, to calculate your expected counts, you're going to multiply the column total with the row total and then divide it by the total for the entire one. So for the first one, we would do 910 times 131, and I'm going to divide that by 1537, and that'll tell you what should go in this block on your new table. So for main campus, we can calculate this monthly, daily, and weekly and get all of our values. And Commonwealth campus, we can calculate monthly, daily, and weekly as well. Calculate the chi-square statistic and show your work. So we have the 2 tables. Remember, to calculate the chi-square statistic, you don't have to show every step, but you're going to start with the ones in there in the same places. You're going to do observed minus expected squared all over the expected value. Plus, we'll do the next one, observed minus expected squared all over the expected. And you would do that for all the values until you get to the last one, which would be observed minus expected squared all over the expected value. And that should give you a chi-square value of 19.49.